Okay, in this video, I'm going to do problems 10 through 18 on the topic for test review. So again, I think all these have one. Yeah, so I'm going to go through each of these problems in this video. So for number 10, we're simplifying square roots. And so what we want to do is factor these square roots and get them simplified. Remember, I can't actually add these together until they have the exact same thing inside the radical. So I have to have the square root of the same number. So if I'm thinking about the number 45, I'm going to just break this down with perfect squares. So that's 9 times 5. And we know the square root of 9 is 3, and the square root of 5 stays. So this is going to be equal to 7 times 3 radical 5. So 45 square root is equivalent to 3 radical 5. Again, you could do that using the hockey stick, but sometimes it's a little bit faster just to recognize what perfect square goes into that. For the next one, we have -6 times square root of 20. So if we kind of use that strategy again for 20 has a perfect square factor of 4. It's 4 times 5. And so the square root of 4 is 2. And the 5 has to be left inside the radical. So it looks like we'll be able to combine these because they have a square root of 5. So hopefully this last one also has a square root of 5. So plus 2 times the square root of 125. And so 125 is 25 times 5. And again, 25 is a perfect square. So the square root of 25 is 5. And then there's a 5 left in the radical. So again, I did this a little different than we did in the notes because we didn't use the hockey stick, but really just knowing what perfect square goes in works because these numbers were small. If the numbers are big or you aren't familiar with their factors, remember what we did is we looked for the prime factorization. So for like 45, what we would have done is said, okay, 2 doesn't go in, so let's not even try it. 3 goes into 45 and we're left with 15. And then 15 is 3 times 5, and then 5 is 5 times 1. And so for the same reason, the 3 left the radical, right? Because I knew the square root of 9 was 3, or there's a pair of 3s. So you can still use that strategy. I was just trying to save some space on the paper. So what we want to do now is simplify. So 7 times 3, we can't multiply with the 5. The 5 is just going to carry along is 21. So 21 times the square root of 5. Minus 6 times 2 is 12 times the square root of 5. And then plus 2 times 5 is 10 times the square root of 5. So now that they all have that same radical 5, I can just add the coefficients. So 21 minus 12 plus 10 is going to give us a sum of 19 radical 5. When we're multiplying variables together and they have exponents, this is something that was kind of complicated, but we'd left off the quiz and we said would be on the test. I'm multiplying coefficients together and I'm multiplying the bases, same bases together. So that means that I'm thinking about these as two separate things. So I'm multiplying -4 times -7. That part's straightforward. And that gives us a positive 28. But what I'm also doing is I'm multiplying x to the 4/7 power times x to the 1/3 power. And to do that, what I'm doing is I'm doing x to the 4/7 plus 1/3. So to combine these together, I'm multiplying my bases, so I need to add my exponents. So I'm going to do a little bit of side work just so that I don't take up a bunch of space in the exponent and have to write extra small. If I'm adding 4/7 plus 1/3, I need to find a common denominator. 7 and 3 are both prime, so I'm going to multiply the first one by 3/3 and the second one by 7/7. So what I have is 28x, and 4 times 3 is 12, over 7 times 3 is 21, plus 1 times 7 is 7, over 7 times 3 is 21. And so that means that 28x is equal, it's equal to 28x to the 12 plus 7, so 19. over 21 power. Remember that if that numerator was larger than 21, I would have to simplify it and look at it in terms of a radical, but since it's lower, I can just leave that as the answer. Okay, so question 12 is something that's similar to what we had on the quiz. So this is a problem where we need to check for extraneous solutions because we have an x on both sides. So that's the instance where we can come up with answers that aren't actually solutions to the original problem. We start by squaring both sides so that we can get rid of the square root. So by squaring both sides, we're really multiplying x minus 5 times itself. And on the other side, all that does is cancel out the radical, so we're left with just 2x plus 5. So if I multiply out x minus 5 times x minus 5, I'm going to get x squared minus 5x, and then minus 5x. Oh, I didn't change colors. Sorry, minus 5x. Oops. Plus 25 is still equal to 2x plus 5. And so for these problems, remember, we want to factor. So what we're going to do is move the 2x and the 5 over to the other side. We want this equal to 0 so that it's something that's factorable. And so our answers are going to come from the zeros of those factors. So if I combine like terms, I've got x squared, and then all my x's together is going to make negative 12x. And then 25 minus 5 is 20. So I'm doing here a product sum, what multiplies to 20 and adds to negative 12. So the two numbers that will work are negative 2 and negative 10. So that means this factors to x minus 2 times x minus 10 equals 0. So from this, we have two potential answers. X is either going to equal 2, because 2 minus 2 is 0, or x is going to equal, or x is going to equal 10, because 10 minus 10 is 0. Remember that we have to check this in the original problem. Our original problem is x minus 5 equals the square root of 2x plus 5. So I'm going to write that out twice where I have some space to simplify. And so if I plug in 2 minus 5 is negative 3. The square root of 4 plus 5 is the square root of 9, so that's positive 3. So notice that negative 3 is not the same as positive 3, so 2 is not an answer. Hopefully 10 is an answer. If it's not, then we have no solution. So 10 minus 5 is positive 5, and then 2 times 10 is 20, plus 5 is 25. The square root of 25 is positive 5, so that one worked. So our only answer here is 10. So remember that every time we have an x on both sides with the radical equations, that's when we have the possibility for extraneous solutions, versus in number 3, we only have one x, so we shouldn't have an extraneous solution. Oh, sorry. Okay, so for number 13, we're solving. And so this came from day 2 of 4-4, where the big idea was taking the reciprocal power to both sides to cancel out a fraction power. So I'm going to rewrite the problem. X squared plus 12x plus 39 raised to the 3 over 2 power equals 8. And again, our strategy is to raise both sides to the reciprocal of that power, so to the 2/3 power. The big idea there is that our powers cancel here because we're multiplying, and so we're left with x squared plus 12x plus 39 equals. So remember, you can use your calculator to evaluate 8 to the 2/3, or you're going to have to think about it as a cube root of 8 squared, like what we did in problem 1. So the cube root of 8 is 2. 2 squared is 4. So this is equal to 4. If you do this and you don't get a perfect cube or square or whatever, if you don't get an integer, that means that your power's flipped. Okay, so if you're using your calculator, it might be that you input it incorrectly in the calculator. But if you're doing it by hand and you don't get a perfect number, an integer out, that means that you should probably do the reciprocal here, that you use the same value here instead. So then in order to solve for x, we have to do what we did in the last problem, which is get it equal to 0 and factor. So if I subtract 4 from both sides, x squared plus 12x plus 35 equals 0. So I'm looking for two numbers that multiply to 35 and add to 12. So for this problem, those numbers are 5 and 7. So this factors to x plus 5 times x plus 7 equals 0. So these tell us that the answers are -5 because -5 plus 5 is 0, and -7 because -7 plus 7 is 0. Okay, so then for problems 14 through 16, we're using the same two functions and we're doing different operations. So for 14, they're asking us to find g of f of -3. So remember, this is where we work backwards. So we're gonna plug -3 into f to start. So we're gonna start with f of -3. F of -3 is -3 minus 3, which gives us an answer of -6. Okay, we're building. So now we're going to take this answer and we're going to plug it in to get g. So we're doing g of -6. So 2 times -6 squared minus -6 minus 15. So 2 times -6 squared is 2 times 36 plus 6 minus 15. So 2 times 36 is 72, and then 6 plus 15 is -9. And so that means that this answer is 63. So g of f of -3 is 63. So again, that's the kind where we build. So we plug -3 into f, we get an answer. We plug our answer into g, working from right to left. Find g of f, g over f, and state the domain. So g is the equation 2x squared minus x minus 15, and f is the equation x minus 3. For these problems, we always have to simplify, and so simplifying means I need to factor. So when I'm saying the domain, what I know is that the domain is all real numbers except the value that would make the denominator 0. So if that x was a +3, that would make the denominator 0. So that's my domain. I have to factor 2x squared minus x minus 15 in order to tell what the simplified g over f is. So remember that we're taking a times c. So a is 2 and c is -15. So we want two numbers that multiply to -30 and add to b, which is -1. So the two numbers that will multiply to -30 and add to -1 are -6 and +5. So what we're going to do is take our original equation, so the 2x squared minus x minus 15, and we're using the -6 and the +5 to split up the -x. So we're going to do -6x plus 5x, and we have to use grouping to find our factors. So if I split that in half, the first two terms have a 2x in common, and so if I divide by that greatest common factor, I'm left with x minus 3. Oops, that's supposed to be a 15. So I knew that I wrote something wrong because I know I'm supposed to have an x minus 3 here. And if that was a 5 like I had written, it would have been an x minus 1. So be careful that you copy that down correctly. So the last term should be negative 15, and I made that mistake. So the first two terms had a common factor of 2x. The second two terms have a common factor of 5. So I'm going to put plus 5, and then I'm dividing both terms by 5. That's going to leave me with x minus 3, just like the first one. So that means that the factors of 2x squared minus x minus 15 is x minus 3 times 2x plus 5. So remember, the 2x plus 5 comes from the combination of those two GCFs. And so that's over x minus 3. And so I can reduce this fraction by x minus 3, which means the answer is just the 2x plus 5. So g over f is 2x plus 5, and the domain is all real numbers except 3. F minus g means I'm taking the equation for f, which again was the x minus 3 equation, and I'm subtracting the equation for g. So g was 2x squared minus x minus 15. Remember that it's important that we put it in parentheses because this negative means that each of these signs are going to change. So I'm distributing that negative through there so that I can combine like terms. So I'm only changing the signs of the expression after the negative, and then I'm going to combine like terms. So our first term should be x squared. So that gives us a negative 2x squared. If we combine the x's, we have plus 2x. And if we combine the constants, we have plus 12. So this answer is negative 2x squared plus 2x plus 12. The last two problems are the graphs. So I'm going to go through kind of the initial way that we graphed, and then we'll talk about the patterns and give you the pattern table so that you can choose which method you prefer. And so when we are graphing a square root, remember that our goal was to try to get this inside piece to be a perfect square. So this equation's a little bit longer. So the fastest way really to do this is to use a, h, and k. And so looking at our equation, a is 4. H is the opposite of negative 3. And so that means h is positive 3. And k is negative 2. So let's just use the patterns for the sake of time, because this is a long equation, versus for 18 we can talk about using just trying to make perfect cubes. So if I'm graphing a square root, I only have to do 3 points. Your table will have how many you need. The first point is the HK point. So that means that the first point has an x value of h, because when I plug in 3 to there, it gives me 0. Remember, our goal is to make the square root of 0, the square root of 1, the square root of 4, because those are our first 3 perfect squares. To find the consecutive y values, remember that we're adding a. So we're going to add 4, and we're going to add 4 to get the y values for our graph. So negative 2 plus 4 is going to be positive 2, and 2 plus 4 is going to be 6. And then because square roots and quadratics are inverses, remember the x and y are switched, so our y pattern that we're used to for quadratics is actually our x pattern for square roots. So to get the next x value from h, we're going to add 1, and then we're going to add 3. If we wanted to find another one, we would add 5, and then we'd still add 4 on the y values. So the 3 points that we're graphing are 3, negative 2, 4, 2, and then 7, 6. So we're off the graph a little bit. So this is the graph of 4 times the square root of x minus 3 minus 2. For 18, I think it's easier to just look at it in terms of what makes the perfect cubes. And so for the middle piece, that's where our 0. So if we're thinking about the table, what we want our x, the piece under the radical to be is, we want the piece under the radical to be -8, -1, 0, 1, and 8, because that's -2 cubed, -1 cubed, 0 cubed, 1 cubed, 8 cubed. And so the number that I would have to have for x to make the inside -8 is -4. So -4 minus 4 is going to give me -8. And so then when I plug this in, oh, I should have cube roots here, sorry. Then when I plug this in, the cube root of -4 minus 4 simplifies to the cube root of -8, which is -2. So my first point is going to be -4, -2. Then I want this inside the radical to be -1. So that means that I need to have a +3. This 3 minus 4 makes -1. So that the cube root of -1 is -1. So my next point is going to be 3, -1. For the next point, the middle point, I want the number to make 0. This is the one where this is going to be our HK. So notice that in this equation, H is, oops, I always do H in blue. H is 0. Sorry, H is +4. And when I plug 4 into there, 4 minus 4 makes 0. That's going to be the cube root of 0. And so what ends up happening is that that equals 0, which is actually our K value. So then if we want, our next perfect cube is +1. So if I want this to be +1, I need to plug in a 5 for x. So 5 minus 4 is 1. So the cube root of 5 minus 4 is the cube root of 1. Oh, I forgot to plot that point. So 4, 0. And then we just did 5, 1. And then for our last point, we want the part under the radical to be 8. So since it's +8, I have to plug in +12. So 12 minus 4 is what's going to give me 8. So 12 minus 4 is 8. And the cube root of 8 is 2. So over here at 12, it's going to be at 2. So my graph of a cube root function always looks like this, kind of S shape almost, with those 5 points. So remember that what we did with a square root, it's a lot easier to set up the table using A, H, and K. I'll refresh your memory on what that is here. So for a cube root, the middle one is the HK. And then if we think about these numbers and how I want to make -1, I'm subtracting 1 here, but then I'm subtracting 7, and I'm adding 1, and then I'm adding 7. So this is not quadratic, so it's not following the pattern you're used to. So that's why I don't think it's necessarily the best way to do this, but if you're good at memorizing, it's 1 and 7. When I go up, I always subtract. When I go down, I always add because of that nature of I'm starting in the middle. So K is in the middle. And then it works the same way as the square root, where to go up and down here, I'm using the A value. So again, if I'm going up, I'm subtracting A. If I'm going down, I'm adding A. So our A was 1. Notice all these increase by 1. So if I subtract 1, add 1, that's the case. So that's our generic equation table for a cube root function. So again, because I'm looking for these perfect cubes, my pattern is 1, 7 instead of 1, 3. So whatever kind of helps you do the graph, that is the final type of question, aside from the bonus, which you won't see a preview of for the topic 4 test.